MIT applied the concept of toroidal propulsion to drones, implementing a looped-back configuration. Similarly to its application in other areas, this arrangement demonstrated an instant reduction in noise within the frequency range of 1 to 5 kHz thanks to the increased focus of the vortex. There is conjecture that this design might generate greater thrust at a given power output, but its potential can only be fully realized through refinement and extensive testing. Exploring unconventional propulsion systems for drones, we delve into a range of options from rotary cycles to jet engines and even artificial gusts. One of the most intriguing concepts originates from Leonardo da Vinci's aerial screw designs, which have now been revitalized. Initially simulated, this design revealed captivating vortex patterns, leading the University of Maryland to develop an actual flying drone based on this idea after months of testing. With proper optimization, this craft could mitigate noise disturbance and potentially operate with less noise than conventional propellers. However, the complexity of the design, coupled with limited improvements in lift efficiency, suggests that it won't displace the propellers in the near future. Nevertheless, witnessing the successful application of the aerial screw to drones remains a fascinating feat. DARPA's involvement in an active airflow system under the intriguing name Crane evokes memories of the speculated top-secret aircraft Aora. Rather than relying on moving parts, this prototype harnesses banks of air nozzles linked to a pressurized system. This innovative setup enables it to expel air forcefully and effectively modify the airflow and air pressure surrounding the aircraft. While it currently cannot create virtual surfaces using compressed air, DARPA is constructing a 7,000-pound UAV for test flights at a speed of 0.7. It's highly likely that DARPA is also observing NASA's morphable wanes, which are considered mechanical metamaterials capable of reconfiguration during different flight phases. The aircraft of the future may combine air nozzles and a morphing composite wing, offering potential performance enhancements that would be truly captivating to witness. Let's veer off course for a moment and delve into a distinct propulsion system known as the Cyclorotor, akin to a paddle boat navigating through water. The Cyclorotor operates by accelerating fluid with a perpendicular rotating mechanism, resulting in an orbital motion and pitch angle that generates significant thrust. Additionally, individual blades can be pitched, enabling swift thrust vectoring. Complexity stands out as a major drawback of the Cyclorotor, leading to higher costs and a heavier setup. Nevertheless, this propulsion system finds value in various hybrid applications, such as the exceptional example of the Austria. Unlike a multi-rotor that relies on pitching to alter its horizontal position, the Astra can simply incorporate a cyclorotor on top without any pitch adjustment, making it highly practical for specific tasks like inspections or remote equipment operations. While cyclorotors are unlikely to replace propeller-based systems in the foreseeable future, they hold potential for deployment in hybrid scenarios that necessitate enhanced stabilization. The concept of a cyberphysical macromaterial presents a captivating glimpse into the future. This innovative idea involves using drone builders to stack modular magnetic units, each equipped with sensors and RF devices. Multiple UAV builders communicate through a hierarchical system overseen by a central command processor to coordinate the entire project. Users can configure the layout using a smartphone app, or the material can autonomously adapt, such as by adjusting to sunlight exposure. However, a notable drawback is the limited flight time, suggesting the potential benefits of incorporating module units capable of independent movement. Among the most peculiar contenders in the field of propulsion is Ionocraft, utilizing ion propulsion. Electrohydrodynamic (EHD) thrusters generate a plasma of ionized air using a high-strength field. The ions are attracted to a negatively charged grid, colliding with neutral molecules and imparting momentum. Initial experimentation with a small 2 cm squared prototype revealed an intriguing discovery. Scaling down EHD thrusters actually improved the thrust-to-weight ratios. This makes it a potentially viable option for micro-aerial vehicles, although practical implementation has been challenging due to the difficulty of integrating a high-voltage power supply on board. Ethan Cross has developed a large RC vehicle with its own power supply, continuously working on advancing this concept for wider applications. Another noteworthy project is Juventus, which combines ion stabilization with a ducted fan for reduced noise levels. While both projects are still in progress, no groundbreaking developments have emerged thus far. Ion propulsion is captivating due to its absence of moving parts. However, incorporating an onboard power supply remains a complex endeavor, resulting in limited maneuverability for these drones. Basic versions of ion-driven robots are sluggish and lack the performance characteristics of traditional drones. Nonetheless, newer micro-aerial vehicles are emerging that circumvent the limitations of conventional motor and gear designs, offering potential advancements in this field. Thanks for watching. What's your take on the evolution of drone propulsion? Let us know in the comments below.